One qubit is good, but there's not much problems we can solve with it. For the real computational problems, we need more. And at first glance, this does not present any problems. Photons, electrons, silver atoms, we have plenty of these. If we need, for example, 1000 qubits, we can easily generate 1000 photons, right? And if we do, it is no problem for us to generate all those photons in the superposition state, the state plus, for example. Imagine we did that. Now, if we measure all these 1000 photons, each in 0, 1 basis, then how many possible outcomes can we get? The answer to this question is really amazing. Each photon can randomly collapse to one of the basis states, which gives us 2 opportunities for each photon. And for thousands of photons, we would have 2 multiplied by 2 multiplied by 2 and so on 1000 times opportunities. It is 2 in the power 1000, which is quite a big number. This number has approximately 300 decimal digits. To understand how big this number is, let's recall that the number of all elementary particles in our universe is estimated by physicists with a number with less than 100 of decimal digits. And adding just one more digit to it roughly multiplies it by 10. And for our number of outcomes, we add more than 200 digits to that horrendous number. And what is this number with 300 digits? What is its physical meaning? Well, since it is the number of all possible outcomes, it is the size of the basis in the state space of the considered system. Our system with just 1000 of photons is described by a vector in the state space of this dimensionality. Does not it look awesome? And in general, the dimensionality of the state space of n two-level particles is 2 in the power n. This gives us almost unlimited computing power. By adding just one particle to it, we can double the dimensionality of the state space. So why don't we use it right now? It is indeed the good question. To answer it, we need first to recall how we use data in the classical computations. Most of the algorithms do not process bits of data separately. Processing of parts of information almost always depends on other parts of information. Consider an example of adding 2 numbers, say 13 and 18. Let's do it with the column method we learned at school. First, we add up 3 and 8. School teacher tells us to write down 1 as the part of our answer, and another 1 on the place for tens we must keep in mind. And when we are ready to add up tens, we have to remember that we kept in mind this 110, which we obtained by adding 3 and 8. This means that in this algorithm, the result of adding up 2 digits on some decimal place depends on the previous additions for the previous decimal places. So, in our hypothetical computer based on photons, processing or changing the states of some photons will depend on the states of another photons. And as we remember, we cannot read those states, because in that case, those states would collapse and destroy the superposition, which was the source of all our magic. It looks like photons have to read the states of other photons without our help. Imagine 2 photons, A and B. Now imagine that we can make photon A to read the state of photon B. And not just to read, but to change its own state accordingly. We want photon A to flip its state if photon B is in the state 1, and we want it to do nothing if photon B is in the state 0. By flipping, I mean changing its value to the opposite, 0 to 1 and 1 to 0. The described operation is called conditional NOT. We apply the gate NOT to photon A based on the state of photon B. Please note, we ourselves do not read any of these states. For us, the state of B does not collapse. So let's assume we can perform this operation. From now on, we will call it C0, which is short for conditional NOT. Now, let photon A be in the state 0 and photon B in the state plus, which is the superposition of 0 and 1. What state will we obtain after applying this C0 gate? Let's see. From the multiverse perspective, photon B exists in two different states simultaneously in different universes, the states 0 and 1. Photon A also has many copies in multiverse, but for now those copies are identical. But when photon A interacts with B, it subjectively observes different copies of B, so its own state stops being identical. The copy of A which observed 0 does not change, but the copy of A which observed 1 flips its state to 1. And we finally have this state. This state is one of the famous Bell states. It describes the state of a two-particle system, but the most astonishing fact about it is that these particles do not have their separate states. You can't say now which state has photon A or photon B from now on. It is like a superposition, but not for a particle, but for a system of particles. Though the particles are separate and can be even very far from each other, their states are like glued together or entangled. Entangled is the right term for this type of states. And the operation we have just performed on paper, the C0 gate, is an entangling operation. To perform meaningful computations, we need to be able to implement this operation with any two particles of our system. So can we implement it? Not so well. I don't know any experiments of implementing C0 with photons polarization, but there are some positive results with other two-level systems, like Rydberg atoms. These are the atoms with a very big radius. A big radius is important because we have a physical contradiction here. We need particles to be far enough from each other so we could control their states separately with, for example, a laser beam. But we need them to be close enough to each other so they would be able to interact and construct these entangled states. Big radius of atoms allows us to control them separately when they are placed near of each other. And of course, there is no way we can arrange these atoms in the physical three-dimensional space so they would be able to form these entangled ensembles in any desired order. There can be only limited number of close neighbors for each atom. So, with implementing entangling operators, at least for now, we have problems. But keep your chin up. Physicists work on this.